Hello, my people. I hope we're doing well today. As we venture into the next section, basically we're going to be doing the same thing. We're just going to be adding some more identities. Okay, and I will be posting this particular document for you. And basically, it is a list of all of the additional identities that are usually given in pre-cal books for the trig unit and stuff like that. I have basically divided them into two different categories. Ones that I expect you to memorize and ones that not even I memorize, so I will not require it of you. But today we'll be dealing with this first group right here, the sum and difference identities. Tomorrow we'll be dealing with double angle. I will post a video on where we get these, because we get these from these, right? Basically, I will basically derive for you this cosine u minus v, and the rest of them can be arrived at from that one. In this first video, I will do the derivation of the sum and difference identities. If you were in class or you watched the class video and you don't want to rehash that, then by all means skip on to the second video and just get to the meat of it, where I'll be doing some problems. But let's go ahead. Okay, let me zoom out again. Basically, we're going to be doing the change. We're going to be doing evaluating. We're going to be doing change of form. We're going to be doing verification. And we're going to be doing solving of equations. All of the things that we did with the fundamental IDs, we will now do with this group of IDs as well. Of course, the fundamental IDs will sort of fold in with these because, obviously these aren't one-step problems. They're multi-step problems. And so it's not that we're using these instead, we're using these on top of, okay? But we're going to go ahead and derive this first one, this cosine x minus y, and then I will show you how we can get to the rest of them from there. Now, the reason we do this is, first of all, like I was explaining in class, this gives us an opportunity simply to play with these trig functions. And it's that whole time and exposure, time and exposure, time and exposure that helps us to become good. It helps us become, good, for lack of a better word, good at using these for the multiplicity of purposes that they are there to perform. And so I hate formulas. I hate memorization. And the thing is that if you know where these come from and how to derive them, you don't have to memorize all of them. You simply have to memorize some of them and be able to do the derivation for the rest of them. Even sometimes I kind of, when I'm dealing with the cosecant and cotangent squared Pythagorean, sometimes I'm like, which one is that? Which one's this difference? And basically all I have to do is just go right back to the sine squared plus cosine squared is equal to 1 and rederive it. And then I confirm or disconfirm, what I was thinking. Everybody's synapses misfire every once in a while. And so understanding where all of these come from and their mutual interdependence upon each other is going to go a long way to helping you, not only in terms of being able to remember them, but also just, that's what it means to think mathematically. Formulas are for science class. We do math here. Okay. Now, let's say I have this angle, and I've cut it out of this circle right here to ensure that when I put this angle on these two different circles, it's going to be exactly the same angle. Okay. So let's say that I have the angle right here on this unit circle, and it's important that they're unit circles. Okay. Because we're going to be dealing with the the ordered pairs from where they intersect. Now I missed a little bit, but you get the idea. This right here, let's call this alpha, and this right here, let's call this beta. Okay. Now basically what happens is if that big one right there is beta and the small one is alpha, then this right here is, of course, the difference between the two, okay? And every point on the unit circle is, you know, cosine theta comma sine theta. So this point right here is cosine of alpha, sine of alpha. This point right here, okay, is cosine of beta, sine of beta. Now, the reason you might not understand why we're doing this, it'll become clear here in just a second. Let's go ahead and let's take this angle that we're really interested in, this beta minus alpha, and let's go ahead and put it in standard position, meaning that its initial side is on the positive x-axis, okay? Now, it doesn't matter the fact that it's in standard position here and not in standard position over here on this first circle, because either way it is going to be the same exact angle. It's you know, if we've labeled it beta minus alpha over here, it's just as easily going to be beta minus alpha over here. And this ordered pair right here is cosine of beta minus alpha and sine of beta minus alpha. This ordered pair is 1, 0. Now you might be wondering, why in the heck are you drawing the same angle in two different places on two different unit circles? I get what you're doing. I'm failing to understand why. Well, here's the why. If I have equal angles, then the chord that extends between the points of the initial and terminal rays of that angle should be the same distance, right? This, let's call it D, and this is the same distance since they're both unit circles and it's the same angle, right? Okay, well, we can use the distance formula to find the distance of that. And since both of those have two distinct sets of ordered pairs with which we can actually get the distance formula, then we can set those different expressions of the distance equal to each other. Now, remember that the distance formula is just the Pythagorean theorem in disguise. So I'm not going to look for D. I'm going to go ahead and look for D squared, because if I look for D, then I have a radical, and then I'm going to set two radicals equal to each other, and I'm just going to wind up squaring them back out again. So I might as well deal with D squared, okay? So this first one, D squared, that tells me that, let's deal with the x coordinate first. We have cosine beta minus cosine alpha squared, right? X2 minus x1. And then we have y2 minus y1 squared, and that should be D squared, okay? I'm going to go ahead and draw a line down the middle here. Okay, now over here, this ought to be the same distance, right? But we can express it differently. And we have x2 minus x1 squared, and then y2 minus y1 squared. Okay, and for those of you who are still failing to see the import of this, let's go ahead and expand it out. Now I need to FOIL out this and FOIL out that, so expand both of those binomial squares, and I'm going to get cosine squared beta minus 2 cosine alpha cosine beta plus cosine squared alpha. And then, of course, I'm going to have to drop down to a second line right here just because there's not room. Sine squared beta minus 2 sine alpha sine beta plus sine squared alpha. Over here, I don't have quite as much notation because one of these ordered pairs was just 1 and 0, right? 2 cosine of beta minus alpha plus 1, and then of course there's the sine squared beta minus alpha. Now, there's a whole lot of sine squareds and cosine squareds, and they're all positive, which means that these two right here can link up and become 1. These two right here can link up and become 1. And these two right here can link up and become 1. Okay, well that simplifies things nicely. And so we're going to get 2, because this is 1 plus 1, minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. And we're going to set it equal to this d squared over here. And so we're going to take this 1 from the Pythagorean and add it to that 1, which was a constant. And we're going to get cosine beta minus alpha. Okay. Now, there's a little bit of simplification that can be done here. First of all, let's go ahead and subtract 2 from both sides. And once we've subtracted 2 from both sides, everything has a common factor of -2. Let's multiply through by -1/2. And what I'm going to get, and I'm just going to swap the sides here, we're going to get cosine of beta minus alpha is equal to cosine alpha cosine beta plus sine alpha sine beta. Okay, and there you go. And all I'm going to do here is I'm just going to replace, my x for beta, my y for alpha, and this gives me cosine x cosine y plus sine x sine y. And I swapped the order of those because within these terms, they're products and they're commutative, so I can put them in any order, right? I could have put cosine y cosine x plus sine y sine x, but it doesn't really matter. Now, that's the first one. Now, that's the only one that is actually all that difficult. The rest of them are going to come from here. In fact, basically, this whole sheet comes from this one right here. And I'm going to show you what that means, okay? Alrighty, so we're going to go from cosine of x minus y to cosine of x plus y. And here's how we're going to do it. Now remember that anytime you had something like, 4 minus a -3, well, when you subtract a negative, it's the same as adding, right? Well, the same is true in the opposite direction. Adding is the same thing as subtracting a negative. And therefore, now that I have sort of rewritten this cosine x plus y as a difference, I can now use the cosine of x minus y. Or, if you want to think of it in terms of variables, think of it as the cosine of u minus v, okay? Now that you can use this, I simply have to plug in, just like the last one, I have to plug in, but instead of plugging in for y, I'm plugging in -y. So this becomes cosine x cosine -y plus sine x sine -y. Now the great thing about cosine of -y and sine of -y is we already know our even and odd identities, okay? And I know that cosine is even. So cosine of -y is the same thing as cosine of y. But I also know that sine is odd. So sine of -y is going to be negative sine of y. And as a part of this term, it's going to change the sign, S-I-G-N, to negative for that entire term. And I'm going to get cosine x cosine y minus sine x sine y. Okay. And you're like, okay, well, that was really clever, but how in the world, Mr. Forth, are you going to turn cosine into sine? I'm so glad you asked. Alrighty. I know that what I'm going to do is I'm going to take cosine of pi over 2 minus x, okay, and then I'm going to add y. Now, here's the thing. Or actually, I kind of messed that up. Okay. If I have sine of x minus y, that is the same thing as pi over 2 minus x minus y, right? Because they're cofunctions, right? What I need to do is I simply need to take whatever, it doesn't really matter. This can be 18 terms long. Whatever this angle expression is, I simply have to subtract it from pi over 2 in order to transform it into cosine. And from here, all I really need to do is distribute that negative and then sort of recombine it as pi over 2 minus x plus y. So, I mean, I was right here. I just sort of got ahead of myself, okay? Now, I simply have to treat pi over 2 minus x as one quantity, and basically what I have here is a different version of that, right? But instead of plugging in x for this cosine and this sine, I'm going to plug in pi over 2 minus x. So I get cosine of pi over 2 minus x and cosine y minus sine of pi over 2 minus x and sine of y. Well, that means that I'm going to get sine x by the cofunction identity, cosine y, minus sine y cosine x. And remember that this is equal to that, and so I have sine x cosine y minus sine y cosine x, and that's how we not only transform cosine into sine, but that's how basically we turn cosine cosine, sine sine into sine cosine, sine cosine. Okay. Now, in this next one, we're simply going to do the same thing we did for going from cosine of x minus y to this one. Okay. We're going to take sine of x plus y, and we're going to represent it as x minus a negative y. And when we do that, basically it's just exactly the same as this, except for instead of plugging in y for this factor and this factor, we're going to be plugging in negative y. Sine x cosine of negative y minus sine of negative y cosine x. And as we've talked about before, cosine is even. So cosine of negative y is the same as cosine of y. Sine, however, is odd, so that's going to change the sign, S-I-G-N, of that second term and turn that difference right here into a sum. So sine x cosine y plus sine y cosine x, and all of a sudden we have both the sum and difference formulas for sine and cosine. Now, what we're going to do from here is we're going to have to combine the sine and the cosine as a quotient in order to arrive at our tangent sum and difference formulas. Now, we should know that tangent of anything, right, is going to be sine over cosine as long as the angle measurement expressions match. Well, I know what sine x plus y and cosine of x plus y are. Sine of x plus y is sine x cosine y plus sine y and cosine x. Here, let me make that a little bit neater than it otherwise would be. And this one winds up being cosine x cosine y minus sine x sine y. Now, I need you to fight the urge to cancel terms, lest I, scream at you and get all red in the face. These don't cancel because cosine y is not a factor of the whole numerator, and cosine y is not a factor of the whole denominator. But I showed you this sheet up at the beginning, okay? And notice that this is a sum over a difference. And what I'm looking for is a sum over a difference. Okay, well, remember when we did IDs like this, there was merely something that you needed to multiply both the numerator and denominator by and distribute to all the terms in order to transform one into the other. Okay, well, basically what that means is I need to take the sine here and transform it into tangent, and I need to get rid of the cosine. Okay, well, and here I need to take the sine and turn it into tangent, and I need to get rid of the cosine. So if I'm looking at the numerator, I know that I need to multiply through by secant x secant y. And the thing is that that's the same thing that's going to help in the denominator. And what I get is when I take this and distribute it to the first term, the sine x and the secant x combine to be tangent, but the cosine y and the secant y cancel out. Okay, same thing happens, but with y, but in the opposite, for the opposite variable here, the secant x and the cosine x cancel, but the sine y and the secant y combine to make tangent y. Now, when both of these are distributed to this first term in the denominator, the cosine x and the secant x cancel, the cosine y and the secant y cancel, leaving you with 1. When you distribute it to the second term in the denominator, the secant x and the sine x become tangent x, and the secant x and the sine y become tangent y, and that is exactly what you get for your sum identity for tangent. Now, when we get down here to tangent x minus y, I could use the sine x minus y and cosine x minus y, but I'm not going to. What I'm going to do instead is I'm going to say, well, that's tangent of x plus a negative y, and that's simply going to be tangent x plus tangent of negative y, 1 minus tangent x, and then tangent of negative y. Well, tangent, like sine, is odd, and therefore what I'm going to get is tangent x minus tangent y, 1 plus tangent x, tangent y. Okay. Now, I hope that wasn't too tedious. I also wanted a place where this was available after this class ends, and if the possibility exists that the videos in Teams, wind up being deleted or whatever, timeout. I wanted a place for you to come back to this if you ever needed it. So I'm hoping that this was clear. If you do have any questions on what I did or why or what's the point or any other questions, please do shoot me an email or send me a message in Teams, and I will get back to you just as soon as I can. Bye.